Hey guys, we are back and we're reviewing for summative number 5 in the spring of 2020 for Algebra 2, so make sure you're watching the right review. The first section on your review and on your test, it's going to be a repeated section from the last test, which was exponential growth and decay. So you're going to be given some functions. So like this one in particular, we have an exponential, and you should be able to tell me this without the graph. It is a decay because your base is smaller than 1. Your base is a 1/4. The horizontal asymptote could be found just by simply looking at the equation. So remember, any vertical shifting is going to move your horizontal asymptote. So this particular one is going to have a horizontal asymptote at y equals -5. So what I'm going to do before I even try to graph anything is I'm going to take my highlighter, and at y equals -5, I'm going to try to draw a line there. That was really bad. I'm going to go ahead and move it down a little bit because apparently I got not the right points. And speaking of points, now we're going to go over to our calculator. So, into y equals, we're going to carefully type in our function 2 times 1/4 to the x power minus 5. One day my calculator will come up. Just a minute. Okay. There we go. Alright. So, y equals... I forgot. I think it was 2 times 1/4 to the x power minus 5. Make sure the minus 5 part of this is out of the parentheses. Otherwise, it's going to think it's a horizontal shift. We'll talk about that a little bit more in a minute. As far as points go, there's a whole lot of points, but only a few that are even worth plotting. Like -1, 3 is nice, 0, -3 is nice, and after that, I'm not going to plot too many more. I forgot what they were. -1, 3... No, that's not right. -1, 3, 0, -3. There we go. 0, -3. I think there was another nice one out there on the list. 6, -5 sounds good. Oh, but that's not actually at -5. It's going to be at just before -5 because that is the location of the asymptote. So, don't be tricked by your calculator. Your horizontal asymptote is at y equals -5. So now that I have a nice graph, I should be able to answer all the other follow-up questions, starting with domain. Well, domain for an exponential function is -infinity to infinity. It goes forever to the left and forever to the right. The range is the one that's a little strange. Your range is going to start at your horizontal asymptote, so -5 to infinity. And then for end behavior, remember I'm always asking about the left side and the right side. So this first one, the way I set it up is left side. And what I had to do for some of you guys on the test, I had to literally draw the word left on your graph. This right here, this is the left side. So it is going up, up, up. So I'm going to write infinity. And then obviously this means the right side then. So again, on the right side of the graph, for some of you I had to write the word right. So be careful here. On the right side, what height is your function approaching? Well, it's approaching the height of the asymptote. So it's trying to approach or get close to -5. So a couple of things to note about these functions is that special number -5 should show up a whole bunch of places in your answer. So I really encourage you guys to recognize that and maybe even highlight it. So -5 is going to show up in your end behavior. It's the asymptote, obviously. It's going to start off your range. So those numbers should all match. And if they don't match, then we're going to have some problems. All right, same style question there. I'm going to move ahead. Let's take a look at number 3. It says, when looking at the function's equation, how can you tell if it's growth or decay? So if it's growth, that means that your base is greater than 1. So as far as giving an example, give your own example. An example of a decay would be that the base is between 0 and 1. So there's a gazillion examples that you could give me here, guys. So like one example of an exponential growth would be like 3 to the x power. But over here for decay, an exponential decay could be something like 1/3 to the x power. So down here, this is the trick question one, right? Be careful. It says, what about if there's a negative exponent? So you have 4 to the -x power. Well, that really says 1/4 to the x power. And then similarly here, 2/3 to the -x power is really the reciprocal 3/2 to the x power. And then similarly here, 1/5 to the negative x power is really a 5 to the x power. So you have to be careful because a negative exponent will give you the reciprocal of the number. Creates a reciprocal, which I never know if I'm spelling that right, so sorry if I am. So for example here, the 4 became a 1/4, so this is now a decay. 3/2, be careful on that one, it is a fraction, but it's a fraction that's larger than 1, it's 1.5, so that means this is a growth. And then 5 is obviously larger than 1, so that too is a growth. So don't get tricked by that trick question this time. And then now for the question that really messed everybody up, the transformations. So be careful, trust your gut instinct about what transformations do and what they look like. So right here, up in the exponent position, by the x, you're going to see what's called a horizontal shift. So x minus 4 means positive 4, really, so it's a right 4. And then off to the side of your function, this is a vertical shift. It's going to do exactly what you think. So a -2 moves everything down 2. If I keep looking down the page, this is the one that got everybody last time, right? So same function, 7 to the x power from that original one we did. But I want you to shift it 5 units to the right and 3 units up. So your new function, which they want you to call g of x, it starts off the same way. It's got a base of 7, and then up in your exponent, 5 units to the right would look like this, x minus 5. And then 3 units up would be off to the side, and then plus 3. And I'm going to write a big note to my slide readers. I think you should check this on the calculator. I think it would be really brilliant if you guys took the time to go to your calculator and then in y1 put 7 to the x power, and then in y2, what if you put the one that you just created and made sure it did exactly what you think? So what if you typed 7 to the x minus 5 plus 3? If you remember a few days ago in class, we did a little, whoa, I didn't want to do that. We did a little partner activity. Oh, for Pete's sake. Hold on. Gotta move stuff around now. Jeepers. Let's try that again. I guess that's where it was. We did an activity with a partner where, you know, you told them what to type, you checked, and you visualized it on the calculator, and you made sure it shifted to the right and up like you thought. I think that'd be a great idea on this test as well. All right, so here's some new stuff. What I need from everybody is a really good understanding of those transformational formulas. These are not given to you, and you do have to have them memorized. So what I mean by that is the logarithmic form going to exponential form and vice versa. All right, so logarithmic form. It starts with the abbreviation for logarithm, and then he uses like a little b in the base position. And then inside of the logarithm, whoops, which I would like you guys to keep using parentheses for this number, is a number, which we're going to call n. And logarithms equal some sort of an answer, so I'm going to call that a. This is the same as an exponential form, which this is the task. Can you rewrite it? So you say, who's my base? My base is b. This a becomes your exponent. And then whatever was in the logarithm is now your answer. So this is log form. This is exponential form. Your job is to rewrite them, all right? So these first two questions, you're going from log to exponential form. So I always figure out like, okay, well, who's my base? 9 is my base, so I write that down. And then 2, this is my answer, so it becomes my exponent. And it's going to equal whatever was in the logarithm, which is clearly an x. You don't have to do any sort of thinking or simplifying after this step. You just stop once you have rewritten it in that form. Now 7 is the opposite problem. You have exponential form, so you have this guy and you're trying to rewrite it in log form. So I'm going to start by writing the abbreviation for log, and then I'm going to find my base. Well, my base is a 6, so it's also the base of the logarithm. Inside of your logarithm, basically these next two things switch. So the 216 is what was originally in the logarithm, and it's going to equal the exponent. I should have matched my colors up here. Let me fix that. I don't know why, but going to log form is hard for me, so then what I usually do is I immediately throw it back into exponential form, like on my own, and I check that I get back to the original problem. Alright, you do have to have those formulas memorized just to be crystal clear. So these next few questions, they're all log questions, and your brain does not think like a logarithm. So what I need you to do is you're going to figure out what these equal by rewriting them as an exponential question. So you start with the base and you say like, oh, 3 to what mystery power is going to give me an answer of 1. And then you might want to check this on your calculator to make sure you verify it as the right answer, but anything to the 0 power is how you're going to get a 1. That's a bit of a number trick question, so be careful on that one. This guy is very similar, where you're going to start by rewriting it as an exponential. You're going to say 4, the base 4, raised to what power is going to give you an answer of 64. So, maybe you think about it, maybe you test some things out on your calculator, but after a couple of verifying things on my calculator, I find out that that is the 3rd power. Be careful on something like this guy here. You want to know what power you're raising this to, obviously. So you say my base of 8. If I raise it to some mystery power, how am I going to get an answer of 1/8? And the way that you change a whole number or an integer to a fraction is you need to use a negative exponent. So in this case, you're going to keep the 8 as an 8, but you need to flip it around, so the exponent you're looking for is a -1. Alright, so I'm letting you finish a few of those on your own. I think that's fair, and we do have lots of practice on that in our homework check, so you can redo some of those problems if you'd like. Okay, here's another new topic. This time we're graphing logarithms. So remember, your calculator doesn't do a very good job of graphing logarithms. In fact, when I go to my calculator and I type in log of x plus 2, we're going to see some weird things happen on our calculator. So first of all, when I graph and look at it, that looks a little fishy to me. I don't remember ever graphing anything that like stops right here, at least not in this semester. So then I might go to my table and look for some good points, and -1, 0 is a good point, and then if I keep scrolling down a little bit, I think we have a nice point at 8, 1, yeah. So I'll plot those, but the other thing I want to note on my calculator is the first time the errors occurred. So the very first error on your table is at x equals -2. That's a very special number to this problem. X equals -2 is the location of the vertical asymptote this time. So for the vertical asymptote, you're going to look for the first error on your calculator. That's a good way for you to think of it. And it occurs at x equals, -2 Abruzzo. Now, what you might want to connect in your head is that this has a left shift of left 2, and that's why you're going to see the vertical asymptote at -2. So that's the connection for a logarithm to the asymptote, and we're going to see that number pop up quite a bit in a minute. Oh, that's so not straight, but it's going to fix it, kind of. Close enough, right? Slightly move it over. So, I already forgot the points, but I think there was -1, 0, and then at 8, 1, and then my calculator made it seem like it looked like this, and if this is what I graph for my teacher, I'm going to get a really bad score, because I don't understand logarithms. I have to be smarter than the calculator, guys. Oh, geez, that's ugly. And I'm supposed to know. Ugh, yeesh. Okay, I think I just need to erase that. I'm supposed to know that my graph scoots down along the asymptote line, like that, and I have to be smarter than my technology. So sometimes that happens. There's limitations to technology, and your knowledge of the actual function itself is what's important here. Alright, so let's talk about domain. In this case, your domain doesn't go forever. It's going to be kind of cut off by the asymptote. So your domain tries to approach -2 and then goes on forever to infinity. This time your range, even though it's real slow on the right side, your range does go up and down forever. So as far as like looking for connections, let's look at the highlight. The left 2 shift right here is the asymptote. It's also the start of my domain. I'm not going to have you do end behavior. Better write that in black ink. I'm not going to have you do end behavior on the logarithms because they're really weird, so just leave that alone, that concept alone for logarithms. All right, transformations of logarithms, very similar to what you see in every function. So inside by the x, this is a horizontal transformation, and there's a built-in negative. So x minus 3 means right 3. It's nice when things are so predictable in math, right? And then this is a vertical transformation. A negative 4 would indicate a downward movement, so down 4. You should be able to identify those, but you could always graph it on your calculator to get a little insight in case you forgot. All right, and here's the final section. Again, it's new. These are the properties of logarithms, and I think I'm going to back up a screen, and I'm going to write down those properties of logarithms real quick. They're going to be real basic versions of them, but just to kind of clear our minds. So when you have a multiplication question, let me write it out as a times b. How about a times b? That's a times. I don't know what happened. That's the condensed version of a logarithm, but you could expand that into the log of the first thing plus the log of the second thing. So that's the way that property works, but it also works in reverse. So you could have this and you could back up the property and try to condense it. We're going to have you do both on this test. So another property that we learned was the quotient property, where you have a division problem. So it looks similar at the beginning. So you separate them into two logarithms when you're expanding. So it's the log of a, but this time instead of adding the logarithms together, you're going to subtract them. And obviously these are general form formulas. A and B can be anything. It could be 3 things instead of 2 things. It's all good time. And then the last property was really the purpose of the logarithm. I call this the Mario property. So you'll have something like a to the x power. And then this exponent is going to get written down in front of the logarithm. So he's going to bring him down. Now that property in reverse means you can bring the exponent back up. So keep that in mind. So it'd be like x as a coefficient times the log of a. And of course, just to make things really fun, you can combo some of these problems. You can combo all 3 of the problems. So let's look at a few problems in action. I'm looking at number 12. I think it helps tremendously if you put little multiplication dots between each of the terms inside of the logarithm. You have 1, 2, 3 different things you got to break up here, guys. So we could start by breaking this up into 3 logarithms, where you're adding all of them together. Apologies for my sloppy handwriting right now. Inside of each logarithm is each individual thing. So we got like a 5, and then we've got a to the third, which I know some of you already know what to do next. So I'm going to do this in steps. And then you've got b to the second. So we're not done, because anything that was an exponent, to be considered fully expanded, the exponent has to come down in front. So this exponent's going to come down in front of his log, and this exponent's going to come down in front of his log. So this becomes log of 5. That doesn't change, but now it's 3 times the log of a, and then plus 2 times the log of b. So I know I'm done when every logarithm only has one thing inside of it, and there's no more exponents left in the problem. Some of you are so good at this, you can go from beginning to end without any intermediate steps, and that's awesome. I'm not that awesome. All right, number 13. This time we have a natural logarithm. Make sure you understand that that is an L. So I don't want to see I at all, right? That's an ln. When I look at this problem, oh boy, guys, we see a lot of properties. We have a multiplication problem right here. We have an exponent on that, and we also have a division problem. So I think we're going to have to split this up maybe in multiple steps here. I'm going to start by splitting up the division question into a subtraction question. So I'm going to say that's the natural logarithm of the numerator minus the natural logarithm of the denominator. So right now in the numerator I've got a 7 times an x to the third. And then in the denominator I just have a w to the 5th. Alright, so here's what I'm seeing. This logarithm, this first one, still needs to be split up more, because now you still have a multiplication question. So this becomes the natural log of 7 plus the natural log of x to the third. I know some of you see the last step here, but I'm hanging on. And then don't forget, you still have this minus natural log of w to the fifth. So now I go through and I say, well, I'm not quite done yet because these exponents need to come down in front of their logarithms. So this guy needs to come down and this guy needs to come down. Again, if you are an amazing brain who can do this without showing intermediate steps, that's really awesome, but this is a test, so be careful. Alright, so now we got this 3 in front of your natural log of x, and then don't forget this is a subtraction sign here, so you've got a 5 in front of his natural log of w. And that, my friends, is your final answer. That is fully expanded, because every logarithm only has one thing inside of it, and no longer they have exponents. So I prefer condensing. I think condensing is the way to go. When you condense logarithm problems, the final answer should just be a single logarithm, right? So sometimes it helps if I just write that down at the bottom of my paper, where like I know that's what I'm supposed to have at the end. It's supposed to look like this. So all the things we just did, let's do them in reverse. So all those numbers that used to be exponents, you're going to put them back. So this 2 gets put back up, and this 3 gets put back up. So maybe your first step looks like this. Log of 6 plus log of x squared plus log of y to the third. And then what I notice is all of these logarithms are being added together. They're all positive logarithms. So when I smush them all together and condense them into one logarithm, I'm supposed to end up multiplying them all together. So I'm going to take all the things inside of the logarithms, and I'm just going to write them as a big multiplication question. So 6 times x squared times, oops, that was to the third, Abruzzo, third, times y to the third. You do not need these little multiplication dots. Obviously multiplication would be implied, so you don't need them. Alright, I like condensing. I just think it's nice and clean, and it's like picking up your room, right? Everything feels better when you pick up your room. Alright, number 15. We have a natural logarithm this time. Remember, this is a natural logarithm, so that's an L right there. They're going to start the same way. Any exponents need to be put back up in their exponent position. So we have the natural log of x to the fourth plus the natural log of y to the third minus, and then there's no exponent on this guy, so just the natural log of w. So I know when everything gets brought together, it's going to end up being the natural log of some stuff. So that's, I got to work until I look like that. This one's not as easy as the last one because there's 2 positive logarithms followed by a negative logarithm. So maybe it would be smart of us to condense this in stages. Log plus log, this becomes an a multiplying problem. So x to the fourth times y to the third when I condense those 2 logarithms. But don't forget, you still have this other guy over here, so you have minus natural log of w. So when you condense a log minus log, like we have here, this turns into a division question. So inside of the single logarithm, the first logarithm becomes your numerator. Ooh, I can't read. That's x to the fourth. Darn you, reading. That's y to the third. And then your subtracted logarithm, the one with the negative in front of it, that goes into your denominator. And that's how I know I'm all done. Single logarithm, everything's put back together. Again, if you can go from beginning to ending without showing intermediate steps, you're awesome, but it is a little risky on your test, so be careful. Alright, good luck everybody. I hope you all get good scores. I think this is a good time of year to step up, guys. You're gonna have some fun stuff coming up, and the SAT's coming up too, so we gotta be able to focus on some of that. Alright, good luck.